fellow Astro Geeks, and everyone else. I am your host Aditya Sharma from ARKA, the Astronomy Club of IIT Dhanbad. Today we have Dr. V Ramanan sir with us on the very first episode of Primus 2020. His achievements themselves require a complete webinar, so we'll not go into that. I'll just give a brief introduction about him. Dr. Ramanan is currently an adjunct professor at IIST. In the past, he has served as the deputy project leader of Chandrayaan 1, which played a very crucial role in confirming the presence of water on the moon's surface, making India the first country to do so. Before inviting Dr. Ramanan, I'd like to inform you that this session will be having two segments. The first will be the presentation and lecture session by Dr. Ramanan sir himself, followed by a quick Q&A session. Thus, you all are requested to drop your questions in the live chat box below. So, without any further delay, let's invite our honorable guest speaker, Dr. V Ramanan sir. Please take over, sir.
Thank you very much. I'll share the screen. Now, I'll make it full screen. Yes. Hope it's visible to all of you, right? Yeah. Yes. So I will be giving now a talk on mission design and optimization. Okay, that is a topic I have chosen to start the Primus lecture series. Okay, fine. I must thank the organizers first for giving me the opportunity to address you. Just like as I was mentioning, this COVID situation has given it's a blessing in disguise. Right, so we are able to communicate to each other being at home. That's a great thing, with only the positive thing about the COVID situation we can say. Okay, getting into the subject title. Fine. So I start all my lectures with salutes to these architects, great architects. You all know, I don't need to tell stories about these people. You know better than me. Modern science architects, Copernicus, Tycho Brahe, Galileo, who made a lot of observations, and then Kepler, who gave us, apart from making his own observations and using the others' observations, he made empirical laws, 3 laws of motion. Yeah, so that is the starting point, real starting point of modern science, space missions, I would say. Okay, then came great Isaac Newton, so who is the breadwinner for all of us actually in the space industry, and then up to this, all these names will be very much you must be familiar. Maybe next what I have put Lambert, you will understand during my course of lecture why I have put Lambert. Also, he is a great mathematician who is actually real backbone of all space missions actually. Of course, Hohmann is the man who gave the idea even before anybody thought about it. He was the man who introduced this idea of going to Mars, all that as back as in 1920, 1915 itself, that area. Okay, that time. Okay, with this, with my salutes to them, and I will start my lecture. Okay, fine. So when we say space missions, there are many types of space missions are there, going to low Earth orbit, putting a satellite in low Earth orbit around Earth. Okay, that means low Earth orbit means what? Very close to Earth, some 300 kilometer altitude it is going around, or 500 or 1000 kilometers, something like that, very close to Earth. They are low Earth orbit. Then sun synchronous orbit, so which is very useful for remote sensing purposes. Then geostationary orbits, that is very useful for communication purposes, right? Which look stationary with respect to Earth. These are all again Earth-based missions. So there are many. I have just listed a few of them just for your example. Okay, then comes, you can say, deep space missions. Okay. Of this also, some of them only I have put here. There are many things are there, many missions are there. So for Indian context, if you see mission to moon, mission to Mars, mission to a Lagrangian point and low thrust mission. So many missions are there. Deep space mission going to Jupiter or going to Saturn, and so there are missions which are even going beyond, likely to go beyond the solar system. All this is still there in the planning stage. We are still trying to achieve something. Okay. So how we start such a mission? What is the starting point for all these missions? So my main objective is actually to introduce to you all the fundamentals required to just to deal with a space mission design. Okay, that is what. So I would make this presentation somewhat general, and many times it may be little technical. So I think and with the understanding that you are all undergraduate or graduate students or research students, so I have made the talk that way, molded that way. Okay, fine. So if you take a mission, if you want, I want to design a space mission. When I say, the first thing is to think about objective. So objective of the mission, of course, the first objective is I have to reach some planet or some comet or some asteroid, whatever it is. It can be, but there are two things. Objectives can be just a technology demonstration. Yes, I want to prove that I can reach. That is the first thing. And then after reaching just not only technology demonstration, I can do some experiments, scientific experiments, whether some types of what is a gas composition there. All that we can be minerals, what type of minerals are there. So many things we can do that all you know better than me. Certainly, many of your science background will be there. Okay. So first, what we have to start with, an objective and some scientific goals, whatever it is. Then we have to make a vehicle to meet that objective. So that is the next point. Okay, so we have to make a vehicle to meet that. Fine. So when I say space mission design, each mission is unique by itself. There is no, we cannot have a general guidelines, common guidelines applicable to all. It is impossible to give. But we can give broad guidelines which are common to many of the missions. That is what I am going to try today. To introduce to you what are those broad guidelines, how we achieved that in few with two examples I am going to explain to you also. That is the way I am designing my talk. Okay, fine. So when we say space mission design, I said you have to design, first you have to set a goal and then you have to design a vehicle to achieve the goal. Before we start all these things, the first step actually is how to reach. We have to design a trajectory, that is how to reach that destination. That is the first thing we have to design actually. That could be, if it could be optimal trajectory, that means optimal means what? It has to consume minimum fuel or it has to reach in minimum time. Something, some optimality should be there. Something should be minimum. If I am able to do it, then it is a welcome thing. But of course, always just optimal trajectory, optimal path alone will not be sufficient. There will be a lot of constraints, yes, which will actually, we have to take care of the constraints and then optimality will give way for constraints. We have to accommodate the constraints. Maybe I will be addressing that in my, when I go through. Okay. So of course, for all this trajectory, when we start with, we assume that the space vehicle is a point mass. That's a must actually. Otherwise, in beginning itself, you cannot have that as a rigid body. Otherwise, what is the alternative? It's a rigid body. We cannot have that as a rigid body. So we always start with the assumption of point mass. So with this trajectory design, what is the outcome actually? When you just talk about the outcome, it gives you how much velocity you require to reach the destination. Yes, that is a very, very important thing. So how it will be helpful? You want to impart that much velocity to the vehicle, and for that you must provide the propulsion system, and so on. Once your propulsion system design is there, and you other systems to support that also has to get ready. I will be, what are the other systems? Briefly, I will touch upon. Okay. And also trajectory design, not only velocity impulse, it will actually feasibility of a mission it will bring out. How it is actually, you cannot test a vehicle in reality. You know, what is a test? I have made a mission, I have made a vehicle ready, but whether it will work really in the when it is injected into orbit towards the object or asteroid or comet or but we do not know. Only when it is really done, it's a real test actually. So for that, we will simulate the whole scenario will be simulated and seen whether all subsystems are working, whether everything goes as per the expectation, all that. That's what we call a feasibility of a mission. We will be checking all that. So trajectory design is a must to fulfill all these things. Okay, yeah. Fine. Having made this velocity budget ready, now of course I need some initial mass for the vehicle also. Some mass assume, and then you can always change. So as I have told you, we are making propulsion system. Propulsion system can be many things. It can be of chemical propulsion. That is, it can be of solid motor or liquid motor, or cryogenic. You might have heard there is a semi-cryogenic also. Like that, there are many propulsion systems. You can choose one of them to serve your purpose. That is a main thing. Otherwise, if I don't want chemical propulsion, you can go for low thrust propulsion systems like I have ion propulsion, electric propulsion system, right? Ion propulsion system. We say our solar sail system. That also is a low thrust. There are the thrust will be very minimum, less than 10 Newton. But your another parameter which stands for the efficiency of the propulsion system, ISP, that is specific impulse, will be very high for this type of low thrust propulsion systems. So okay, so that we can use the or hybrid mix of these two. All that is possible. You can always, you have to think about your vehicle, your mission, what is the goal, how best you can achieve. You have to make a combination of these and choose one, or it may be a combination of these. All that. Okay. Then vehicle design actually involves, there are so many other things, not only propulsion system, you have to go for structural design. How the structure, whether it is cubical or it should be made of some rods or just a solid structure or just with so many things. But of course, you have to design a structure with some materials properly. That's why I put materials and manufacturing. You have to manufacture it. So only when you manufacture, really, you will know whether that material is really meeting the strength of the material is okay or not. All that will come out only after manufacturing and testing. Qualification is the very qualifying it is the very important step actually. Okay, you have to make a system and qualify it for space. That is the main thing actually. Then aerodynamics may not be there for deep space missions. Of course, if you want to go to Mars and land there, then aerodynamics is required. Suppose just for I want to get out of Earth, I already get out of Earth and I want to reach some comet, no aerodynamics is required. It all depends. Sometimes aerodynamics may be required, aerodynamics may not be required, depending upon the mission. Okay, fine. Then you have thermal systems, very important. You have to keep the whole system, all systems cool. If you know, sometimes your heat may exceed maybe even 1000 degree, 2000 degrees Celsius. So you have to keep your systems within the some temperature levels within which all subsystems will operate. All electronic instruments, your scientific instruments will operate. We have to keep them. Also, power systems which supplies power to the whole vehicle, that also we have to design. Okay, then communication, very important. All is to be made. Without communication, how do we know that where is a vehicle? So we need a communication system. There is S-band, X-band, Ka-band, so many things. Yeah, so we have to make, so we have to choose one of them which is okay for us. We have to do that. Okay, then navigation, guidance, control. These are very NGC we call together. Very, very, very important. Okay, you know, navigation tells you where you are. Guidance tells you where you have to reach. We know, and how you will reach. Guidance will tell. Suppose you have deviated, then how you have to correct yourself. Guidance, it will guide you to the right path. Control will actually realize that guidance path. Guidance advises us you have to take this path, then control realizes that. That is what your NGC system. All these are required to make a mission very successful. And there are other auxiliary systems. This is not a complete list. That will go on. So I will not give the complete system. So now I will stop here and we will go to the other real subject here. Okay. And one point, important point you must note is all subsystems are interdependent. Yeah, so for example, if you take structural design, you want to design, then it will take the inputs from aerodynamics, material, manufacturing, thermal, because aerodynamics, it has go through the atmosphere, then what type of heat it will undergo, and what type of drag it will, frictional forces it will undergo. So it has to know, then only whether your structure will stand or not, you must know. So unless you know that, you will not. So for that purpose only, your trajectory is going to help you to what path it takes. Also is important to know the aerodynamics and thermal things. Okay, yeah, fine. Okay, so next we'll move ahead. Fine. So now we'll see how to design a path. That's what I said in technical terms, trajectory design. So we'll take two examples, and then later on we will explain. We will just describe how to do that. So first, what I said, you have to make a problem clear. Okay, objective. So here, general objective problem statement we can technically we can call. So reach a probe around moon from Earth. You have to reach a vehicle, small vehicle, maybe some mass also you will specify around Earth. I have to reach. That's a first problem I am going to address here. Then land a probe on the surface of the moon. Second problem, maybe just we will address these two problems. How the design actually how the evolves for these two problems. We will see as the lecture goes on. Okay, as the talk goes on. Okay, so now what is the objective here? What can be the objective for the first problem? I have to reach the moon orbit precisely. So moon's orbit, actually, anyway, I'll be talking about how do you represent the moon's orbit in terms of some parameters. So I have to realize those target parameters precisely. That is the one objective here. That can be the thing. What it can be the objective for the second problem? Actually, I want to land on the surface with zero velocity. Yeah, at the time of touchdown, the velocity must be zero. Otherwise, vehicle will impact and break down. Okay, so we have to also, we must aim for a maximum mass actually. That is the thing. I minimize, that means I want to minimize the fuel consumption. That is the thing here. Okay. So, okay, I want to, these are the, one is first general objective, then I want to technical objective, I can say. That's after having set, what is the next step? You have to formulate the problem. You have to formulate the problem. Means what? That is, you have to first set the mathematical model, that is to represent the motion of the space vehicle. That is a thing. Okay, model, mathematical model is a very important thing. So that's what we have to describe the dynamics which will represent the motion. All that, that's what I mean by mathematical model here. Then you have to use probably it's optional, whether it's optimal control theory or not. That it's one of the important thing is actually optimal control theory. You cannot actually exclude optimal control theory from the trajectory design actually. Okay, so but of course nowadays it has become optional. If it is there, there are advantages. They're not there, yes, we can still manage. That is the type of scenario, because there are problems even when we use optimal control theory, so we go for other alternatives. moves also. Okay, that is a situation. Okay. So then having formulated the problem, now you have to look for a solution. What is the solution? I mean, yeah, you must get a design, viable design, feasible design, which will maximize mass, which will realize my target parameters precisely. So that's the solution actually. For that, what is a procedure, what I use, that is I call optimization technique. Some optimization technique I have to use to get the solution. That is the solution procedure I mean here. Okay. Fine. Fine. So I will now elaborate on the for some slides. I will elaborate this formulation and solution approaches. Then we will get into the actual problem. Okay. So when I say formulation, so what you have to do first is actually you have to identify the state variables. Of course, for a space vehicle motion, you know what are the state variables. Immediately you will say position and velocity components. That is x, y, z, where it is, that is position, which is represented by x, y, z, three components, and then with what velocity it moves. So when it is in motion, you need velocity components, x dot, y dot, z dot. These are the states. You have to identify the state variables, whatever may be the problem. I gave one example for a space vehicle, a space motion. But you can do it with any other problem also. You have to identify the state variable. Then you have to identify, second step is control variable or design variables. So we call, both are almost the same. Sometimes we call it design variable, sometimes we call it control variable. That is what we are this one. So design variable means which will actually dictate the path, which will dominate the performance of the path. Same control variable also, same thing. Control variable, how to get into the path optimally. Some variables will control that. That's why we call it design variable or control variable. And then you have to identify the equations of motion. Yeah, let me take some water. Okay. Identify the equations of motion. Okay, that is a thing. Next, maybe you can introduce assumptions to start with because you have to simplify, get the solution, then you can further improve. So first, always we start with some assumptions. Then you slightly relax the assumption, then go for actual solution. That is the best way of attacking any problem. Okay. Then you have to identify what are the constraints during the path. When it goes along its path, some constraint will be there. Like when I am in space, my temperature must be within this level. It should not exceed. The solar radiation pressure is there. It will increase the thermal thing. So we have to control that. There is a constraint on the trajectory. So if it is going that way, you avoid that path. If it exceeds, you have to avoid that path. And also terminal constraint. When I reach the final goal, I must meet the such thing. So for example, for landing, you will say that I must land with zero velocity. Unless otherwise my velocity is zero, all components are zeros, there is no use going and landing. So there is actually that we treat as a terminal constraint. Like this, for every problem you have to identify path constraint, terminal constraints. That comes with experience, of course. Once you look at the problem and you just keep looking at them, you get yourself what should be terminal constraint, what should be path constraint, etc., etc. Of course, identify the boundary condition. See touchdown, when touchdown happens. All this you have to define the touchdown. That is about boundary condition. I will be addressing these things later on. Okay, fine. When I talk about, I said after formulating, you have to look for solution procedure, solution thing. We said optimization. Okay, and before going for optimization, either you can, after formulating, you can decide to go for a solution approach actually here. I said optimal control. Either you can use or you need not use. When you use it, we call it indirect approach. When we don't use optimal control, the theory, then we call it a direct approach. That is the thing. Direct approach or indirect approach. There are two approaches. Of course, following the whether this approach or that still optimization you have to do that. Some only thing I will be addressing what is the difference between direct approach and the indirect approach. Of course, I was talking about of course optimal control theory. Anyway, maybe next thing I will address. Okay, what is a direct approach? We say some orientation of the. Suppose I am going to some space, some any space mission. Actually, how you are accelerating using a thrust, you are firing, you are then you are moving. Okay, but when I want to maximize or minimize something, when I want to optimize something, so what is it I should do? I have to fire such a way that it is optimized. That is a statement I make. So how do I achieve that firing such a way, that statement, how do I achieve actually? That is by setting a direction for the thrust. Okay, that direction for the thrust is the design variable or control variable here in a path actually. So direction of thrust is the control variable, or you can call it a design variable. So here in the direct approach, suppose I take some 100 days to reach the destination, or some time, some term t, some time is there. So then I will first make a guess on the design variable that at this time, after 1 hour, 0 to 1 hour, I will go for this orientation. Thrust will be directed in this direction. Some angle, I will be putting some angle with respect to some local plane. Okay, that is the thing. Okay, so orientation, I mean that only. Fine. So I will be orienting for up to 0 to 1 hour some way, and 1 to 2 hours some other way, and 2 to 3 some other way, some other orientation. Like that, I define. First, I make my guess on the control variable. Directly, I make a guess. Then I go for. Then I simulate with this guess. All control I fire, and I go whether it reaches. First, whether I have to test whether it reaches the destination, then whether it is optimally reaches the destination, I have to see. Two things I have to see. If not, then I have to modify these guesses. This is what your optimization process actually where comes into the picture. This is where the optimization process comes into the picture, where you make initially some guess, and you want to modify that guess because you find that guess does not serve your purpose. It does not reach the goal. It did not, even if it reaches, it does not reach optimally. So that way, then I will have to modify my guess. This optimization technique actually helps you to modify the guess and then arrive at the right value for each of the time instant throughout, so that you will achieve the destination optimally. That is what all this solution approach, direct approach is about. Okay, fine. So one advantage here is anyway that you will understand when I come to the next thing. I will make a statement that there is no co-state here, which we are going to have it in indirect approach. So that because co-state doesn't have a physical significance, I don't know how to make a guess on that. But there is one advantage here because here angles are there. I know what is the angle, physical significance of the angle. I can always try to make a guess. Of course, still it can vary from 0 to 360. You need not know which value. You will not know which value is correct. How you will guess. It again comes through experience and all these things only. Yeah. So this is a direct approach. That way, what happens is the number of points actually plays a role in the number of points means see here 1, 2, 3, 4, 5. If I want to think more points, 10 points or 15 points from here to here, if I do that, then actually the solution accuracy will increase. So, but one problem is the number of unknowns. These are all unknowns, right? What value you should have at some time. Then after 1 hour, what value you should have, I do not know. After second hour, I do not know. If you make every 10 minutes, then your number of unknowns, unknown will be increasing, right? So that is the one disadvantage of this direct approach. So the number of unknowns will be very high when you look for very accurate solution. That is a disadvantage of solution approach, but advantage as far as the current generation is concerned, there are many commercial softwares are available to deal such problems. Of course, you might be knowing FminCon in MATLAB also does that same thing actually. So that is a thing, but for that there are difficulties and all, which I will address a little later probably. Okay, fine. Now, what I said, another approach, indirect approach. Here we say it's formulation is actually is indirect. It is not directly. I am not making a guess on control variable or design variable. Instead, I introduce a dummy variable, fictitious variable called co-state variable. Okay, and then I express the control variable or slash design variable as a function of these co-states, initial co-states. That's it. Initial co-states. Suppose there are six state variables, then I introduce six co-state variables. So then I guess what is a co-state variable? Initially, that's it. We will have co-state dynamics also. We will derive. All these things actually was derived by Pontryagin. Here I have given here Pontryagin and his students. All this theory was developed by him. And it's a very accurate solution you can get through this indirect approach. So advantage of this approach is only co-states are unknown. That is initial co-states. Only six are the unknowns. Okay, like unless unlike in the direct approach, you have so many unknowns depending upon the number of points you choose, depending upon the accuracy you demand. Whereas here you have only at the initial point the co-state variables as unknowns. Once you guess unknowns, then co-state dynamics, which you derive using Pontryagin principle, that takes care of along with the state dynamics. You will know the values, and as a function of co-states, time to time co-states do change, and your control variable you will be getting as a function of co-state variable. You will be deriving an expression as a function of co-state variable. All this was developed by Pontryagin and his students. Actually, this optimal control theory, some of you may be familiar. It is nothing but generalization of calculus of variation. Okay, just as for your information, calculus of variation, you know, calculus is actually function deals with function, and calculus of variation is function of function. Functional, we say, right? That functional, actually here, sometimes you cannot deal with the functional under some situations. Like calculus also, you have a function, suppose you say f equal to x square plus 2x plus 1, and you want to find when the function will have minimum or maximum. What do you do? Immediately you find out partial differentiation. If there is only one variable, you find out df by dx, right? Df by dx, and equate that to 0 and find the x equal to something, your function is minimum or maximum. At that point you declare, right? That is the thing. Suppose you get the solution as x equal to 2, but there is a constraint that x cannot exceed 1. Then how can you deal with that? You cannot deal through calculus, right? So that is the situation. I just explained to you a simple equivalent situation in calculus. That's it. So in the same way, what calculus of variation cannot deal, actually calculus of variation requires that all functions must be unbounded. That whatever I said just now is mathematical terms, we call it bounded or unbounded. So calculus, you can find out, in calculus, you can find out a solution, optimal solution, if it is unbounded only. If it is bounded, then there are other ways of doing it. So same thing here, calculus of variation works so long as the functional is unbounded. When it is bounded, yes, your optimal control theory, Pontryagin, comes to the rescue. Okay, fine, we will proceed. Okay, though we talk about all this trajectory design, optimal, all these things, first thing actually we should aim for is in any mission design, whether analytically whether it is possible to get, instead of going through numerical integration and numerical process, which is a very lengthy, complex, time-consuming process. Okay, so instead of going for that, whether quickly, whether you can get idea about all mission scenarios and you can choose one and you can refine that numerically. That is the best strategy. But it is not mandatory. But only thing, you must be ready to spare time if you want to deal with numerically all scenarios. Okay, it will take a lot of time, unimaginably a lot of time. That's it. Okay, so first, as I told you earlier itself, I addressed this. Closed form solution is the one thing, always welcome thing. Okay, fine. So when I say closed form solutions, it always comes with some assumptions only. Okay, it cannot, just like that you cannot make actually. Okay, so but it helps you to make the generate the design quickly, and you can explore all scenarios, and you will get in-depth knowledge about the whole mission scenarios, and you will get to know what if I do this, what will happen? If I do that, what will happen? So which one is preferable? All that you can explore and choose finally one, and that you refine with numerical procedures. That is the best way of dealing with actually. Of course, some cases, some missions, this will be a possible thing. Some missions, it may not be possible. You have to deal with completely numerically only. In some missions, yes, you can deal with the closed form first, then you can go for numerical thing. That is, both scenarios are possible. Okay, fine. But one more advantage, when you try closed form, your numerically convergence will be very quick. Otherwise, just trying numerical, any numerical process, you all know that who are working on the numerical things, it requires a very good initial guess. That is a thing. So that in the absence of good initial guess, solution may not be coming. Yeah, it may elude you infinitely. Yeah, you may try millions of runs. You try, but still you will be left with no solution. Actually, that is a thing. Okay. So now we'll get into the actual. Quickly, we'll get into the this one. What's the problem one we'll deal with? That is a mission to moon. So what is happening? The steps involved in the mission to moon actually. So you will be first. This Earth here, and from here some launch vehicle push you into some orbit. Okay. Then from that orbit, at an appropriate time, you will be getting into a trajectory which takes you to close to Earth, and when it is very close to Earth, you just get into orbit around moon. That is what steps involved here. So if you want to get into this transfer trajectory towards moon, you have to apply a delta V here, and also after reaching here, you have to apply another that is impulse velocity must be reduced so that it will get captured by moon here. Of course, in between some deviations will be there. That we will correct it. We call it mid-course maneuver. And what I said, the injecting from here towards moon, that is translunar injection. And after getting closer to moon, we get into the orbit around moon. That we call it as lunar orbit insertion, like that. Okay, these are the main steps now. So now, having got that, now I said, what should be the choice of orbit around the Earth? So we have to see. This all again is governed by your launch vehicle capability, and then space vehicle propulsion system. I suppose there is a separate stage to push you into the orbit towards a thing which is available along with the spacecraft. Then it is well and good. Otherwise, you have your choice of orbit is restricted. It has to be, the choice is determined based on that. Okay, fine. Minimum. So this way we will have to, which will give me minimum fuel consumption. Which type of orbit around the Earth will give me, which will require minimum fuel by the spacecraft. That's a thing. Okay, that is a point you have to keep it in mind while designing, while choosing the EP, that Earth parking orbit. EPO means here Earth parking orbit. I don't know whether I will I have some more time after 1 hour. Will it be possible, Aditya? Yeah. Okay, fine, fine. Now I will be now introducing to you a little about orbit. Because we are going to talk about orbit, I thought I will introduce to you some important parameters about the orbit. Many of you may be knowing this orbital. We call it orbital elements. To represent a satellite in motion, you need 6 elements which are equivalent to that position and velocity components. 6 of them we said x, y, z, x dot, y dot, z dot. Then we said what are those things? Same major axis, eccentricity. You know that actually describes the characteristics of the ellipse in which the spacecraft is going around Earth or any other planet. Planetary orbit also you have this, right? Then inclination with respect to equator, how much the orbit is inclined. Then right ascension of ascending node, another parameter. How much it is away from the inertial axis, that is this crossing of the node happens, how far it is happening. This angle explains that. Okay. Then argument of perigee in the orbital plane, where the location of perigee is this angle small omega, argument of perigee that fixes. Then satellites location is represented by the parameter true anomaly here from perigee. These are the 6 parameters which are equivalent to the state vector. Where actually, so this is what we are going to use probably in my lecture. Okay. So now I said in the lunar mission, that is to Chandrayaan 2 or Chandrayaan 1 or whatever it is, what are the design parameters? First, we say that the translunar injection epoch. When I am going to start the journey towards moon, what I said TLI, isn't it? In that slide, you can think that is the thing. When from the parking orbit, when I am going to start my journey into the when I am going to get into the path towards moon, that is a time. That time is unknown. That is a design, one of the design parameter or control parameter. Whatever you, then how much velocity I should increase there, how much I should give so that it will be get into that right path, and what should be the direction of that path, the velocity. Next one, these are all unknowns. This direction is actually determined by 3 parameters. That is right ascension of ascending node, what I said in the previous parameter. Then argument of perigee, that is this is nodal location, fixes the nodal location, this fixes the perigee location, right? How to these two together will fix the velocity direction. All these 4 actually we have to get. Of course, one of the parameter, 2 of the parameters, perigee and inclination, they are actually will be fixed based on the launch vehicle capability. Okay. So then comes the mid-course corrections. They are all also treated as mission design parameters here. Okay, fine. So how do we get that? We said we have to set the next equations of motion. So when we want to go towards moon, what is the equation of motion? You can look at this. This is nothing but inverse square laws, vectorial representation in relative form. Just mu by this GME, you know that this GM is actually nothing but mu e here, GM by r square, that is your this one, your inverse square law. So this is nothing but a vectorial form of the thing. I am giving the direction for the force here, the acceleration here, and that becomes r bar by r. So that is why it is a r bar by r cube. So this equation is the one thing which governs the motion of the spacecraft. If there is only one object is influencing the spacecraft, say Earth, but here there are so many other things here, not only here. So you see here, there is a one first thing is that 2-body motion, only Earth influence here. Then there is an moon's influence, and there are other planets or others, or double dot others actually includes all other things, other planets, and then non-spherical Earth. Because Earth is not sphere, you know, there because of non-spherical, non-uniform gravity field affects the motion. So how it affects, you have to really account for and design. Okay, then drag also. Whenever you are getting into atmosphere of some planet, or you are if you are within the atmosphere of Earth, you have to consider drag also. Of course, solar radiation pressure for any interplanetary mission is a very important parameter. So this is a very complex equation, differential equation, non-linear second order, and which has no closed form solution. Only numerical solution is possible here. So we have to, as I told you, numerical solution is a little complex thing. Actually, you cannot, very time consuming. So where to, I do not know where to start. Initial x, initial y, initial z, I do not know. Initial x dot, initial y dot is initial z dot, I do not know. If only I know, I can check, verify whether I reach the moon or not. By I know I will make a guess on x, y, z, x dot, y dot, z dot, or equivalently, or a, e, I, capital omega, that orbital elements, and try to numerically integrate and see. So like this, how many guesses you will make? So it will become, the problem will become almost impossible to solve. So for that only I was telling, we will go for a closed form solution. A closed form solution starting. That's why I started my salutes with Homan. And so Homan actually gave the initial the thrust. He started with imagined that how to reach Mars here. So this is, he said, Sun is here, Earth is here, and Mars orbit is here. The blue one is Earth. How to transfer? He imagined this type of transfer, but he made two assumptions, that orbits are circular and they are coplanar. With that assumption, he said, you start from here, which is perigee of the transfer ellipse, and reach, when you go and join, that will be apogee of the not apogee, apoapsis, aphelion of the transfer ellipse when you join here. Like that, he made the transfer, and he said this is the optimal transfer. This is a very he's a genius. He's a very great genius. Okay, so the ingenuity you can see here. He just later on there are many proofs. How to prove mathematically is going on. Even now people are doing that, trying to prove this. There are so many proofs. They are already published. Okay, fine. Now moon actually travel is built on this. So here initially I am in an orbit around Earth here, right, and then I have to reach this orbit. I have to transfer to this orbit, and then when I reach here, moon is coming here. I have to design the time such that the moon, when the spacecraft along this orbit comes here, moon also comes here. I have to choose the time, and I have to choose all other things like that, and then design. That is the way you design. Whether Hohmann transfer is sufficient for moon transfer, it is not, obviously, because the assumptions made there is the coplanarity and the circularity. Of course, moon is not moon's orbit around Earth is not circular, and also it is inclined to ecliptic plane by 5 degrees, and to Earth equator it varies between 18 to 28 degrees. Okay, so that whatever you compute the velocity using Hohmann transfer is not sufficient to take you to the moon. So then what next? So you might have seen my next person who took the salutes from me is Lambert. He is the man who introduced this Lambert problem, and he solved that. What is that Lambert problem? Take 2 points in space and fix a time. I say I want to reach the point P1 to P2 in a fixed time, and I want to reach in maybe 5 days or 6 days or 7 days, like that, or sometime, anytime. Then what should be the path? What should be the conic? Conic path means here, what should be the trajectory? Trajectory or conic, what is the difference? Orbit. So trajectory is nothing but part of the conic. Okay, this path is nothing but is going to be part of this whole conic, this ellipse. Here conic is ellipse. Okay, there are various types of conics. You all know that. Hyperbola, parabola, ellipse, all that. Here we are dealing with ellipse for this. Okay, so he actually fixed 2 points, and he derived the solution how to get the path. That is what we are using as the first cut design to going to moon and all that. All analytical procedures depend upon this Lambert problem. Anyway, I cannot get into, because of our time problem, I am not able to get into the details. So those who want to get into the details, they can go through all these papers I have given here. 1, 2, 3, all these. There are so many techniques are there to reach a moon or any other planet also. Pseudo state technique is there. That's analytical iterative past conic, which we recently developed along with my PhD student, and then with my undergraduate student, Ms. Vasis Reddy is here. So all this pseudo state technique is available in this paper. You can go through all these things if you are further interested how to get that. Of course, numerical solution you can get through one commercial software. Satellite toolkit SDK is available. You may be all aware of that. Okay, so these are the. I'm not getting into further into the design and design methodologies. I will just using that type of analytical methods. Now you see here, I have given departure in December 2020. Just first onwards, 31st to go to moon. What is the type of delta V is required? Additional impulse, additional velocity impulse required. At departure, when you depart from Earth, this is the type of variation. It varies from 3 kilometer, the very little variation. Some you see here 31022, 312, 10 meter per second only, not more than that. So TLI, translunar injection, doesn't really matter here. A big difference is not there. Whereas after reaching moon, you have to get around the moon. That is what is really important. There the variation is actually, you see here, 790 to 700, about 70-80 meter per second difference is there actually. Okay, this is a type of variation. Now you choose minimum is here, minimum is here. You say now December 5th, 7th, 8th or 9th corresponds to this point. You choose and then you go ahead like that. But if you consider only TLI, but here we said this is a dominant one. So I have to now consider some of these two. That way the minimum will occur 18th December 2020. For if you design a mission to moon in December, every month minimum opportunity will occur in this for moon. But I said there are constraints. For example, the constraint for Chandrayaan, minimum one important constraint is actually launch vehicle puts into a highly elliptical orbit. You know that. But when it puts the agreement of perigee, that perigee location is around 180 degree. That is a constraint. If you say 160, then launch vehicle will lose payload. It will put less payload. So launch vehicle puts maximum payload for this argument of perigee, some argument of perigee. For this case, for this vehicle, for each vehicle, it will be varying. So corresponding, we cannot just go for that exactly 18th. 18th means here, it comes here actually. In this case, actually, it is around 190 or something, but this is more stringent. So it's only little. 10 meter per second you have to sacrifice. This is more. This is what I meant constraint. So AOP constraint is very important because a vehicle has already given the elliptical orbit of AOP with some AOP. That only you can use. So this is a constraint for further moon travel. So you will choose accordingly. All these design charts. These are all design charts. You will use to choose your orbit, this one, opportunity. Like that, this RAN also, the RAN will decide the liftoff time here. So you will have to choose the liftoff time based on the your time of TLI actually. Okay, so like that. Now coming to, I think I have explained how the general missions happen. Now we'll just look at the Chandrayaan 2. So you know we have pushed into first we have pushed into 45,000, 170 by 40. It's not 40,000. We got 45,000. That's the thing. But planned was 40,000. We got 45,000 here, and then we get into like this several elliptical orbits around Earth. Then finally we started our travel towards moon. So maybe I will address why this by multiple orbits to get into this. Aditya, do I have time? Can I continue for some more time? Are you there?
Yes, sir. Yes, sir. You can go. Sir.
Yeah, sure. Okay. Maybe another 15-20 minutes. Will it be okay?
Yes, sir. It will be okay,
Yeah,
sir.
yeah, it's fine. Okay, so fine. So now I will address why these multiple firings were required for Chandrayaan 2. Why not? Why we did not do it at one go here? Why not we put it to 45,000 and then fire it and go? Why did not we do that? I will be explaining that now. Okay. So of course, launch vehicle puts in a particular orbit, and the velocity from the parking orbit towards moon depends upon the parking orbit in which you are in. You see here, if you are in 300 by 300 circular orbit, you require 3.2 kilometer per second delta V to reach moon from the point on the parking orbit. Suppose you are in 200 by 42,000 orbit around Earth initially. If large vehicle has put you in this orbit, then you require only 600 meter per second to reach moon. That is a type of reduction you see here. That means what? I have to achieve this 3.2 kilometer using spacecraft propulsion system, and which will require a huge propulsion system, which is not you see here in green. I have put we have to use the available resources with India. Okay, so this type of tank capacity to deliver this type of delta V, at present we do not have. So we have, yes, yeah, whatever we have now we can meet this requirement. So we are using the launch vehicle is at the same time is very strong launch vehicle we have, which it can put in a highly elliptical orbit. If, of course, if you ask the launch vehicle to put into this orbit, it will put in instead of 3.5 tons, it will put several 6 or 7 tons in this orbit. But there is no this because we need a spacecraft propulsion system. So instead here we can have we can ask this vehicle to put in a highly elliptical orbit, which makes the demand on the spacecraft propulsion system very less, and that is why we went for this type of highly elliptical orbit. And then why the multiple firings? Even the 600 meter per second, now having put in a highly elliptical orbit, we went with multiple elliptical orbits, then finally we started our journey towards moon. That is the thing. Why we did that actually? I will. This is anyway just whatever I have said. That is Chandrayaan 2's time. 13th August we started translunar injection, and lunar orbit insertion took place on 20th, and the other parameters actually is given here. That's just economic interest. Okay, fine. So now I will explain to you why it was required. Actually, though I said 600, actual thing was delta V required by 557 meter per second. This we are supposed to realize with the spacecraft propulsion system, and for which the thrust level is so 440 Newton, and ISP is 316 seconds. And with this, if you start realizing this delta V, you know rocket equation, you can compute what is the propulsion consumed, and then m dot of this all that you use, you can find out the burn duration, and 4,462 seconds you must burn to realize this 557 meter per second. That means you must start the firing from here. If you want to at one go, if you want to realize this 557, you have to, it's a long arc, because you cannot all of a sudden you cannot achieve. So what 557 actually how we got is we impart instantaneously. That is at this point, perigee point of the ellipse. We assume that it happens all instantaneously, which cannot happen in reality. It can happen over a duration only. When it can happen, if you have a infinite ISP, that specific impulse propulsion system, then you can instantaneously you can impart, which is impossible. So we have a finite ISP propulsion system. So now this requires 4,000 and plus seconds to add this type of 557 meter per second, and then we get into this orbit, which makes actually when you are, that means from the assumption, from the design, that we impart this instantaneously in this direction, we are tangential to this, that is this direction, whereas here when you impart here, this is completely normal to the, this velocity impulse is imparting is normal to the actual direction. It is deviating from the actual direction you require. So the more you get into away from the periapsis, the deviation is more. That means your resultant velocity you are getting into this direction will be less when you deviate more. So it is always preferable you keep the firing as close as to the periapsis here. So that is why it is split into several bands. So each band will have a band, and then it will get into some orbit. Then again you burn very close to periapsis, another orbit, another orbit, another orbit. So how many orbits? All that again is an optimization problem. In how many orbits I should reach? Because here the goal is to reach the translunar. Finally, I should reach the translunar injection at that particular point, at the particular time. Right, that is the time is very crucial here. At that, unless otherwise I reach that translunar injection at that particular thing, the whole geometry for the further travel will be lost. You will be requiring more fuel to that. If you miss the time, you require more fuel. That is a scenario. So I don't want to miss the thing. So I have to do this, all these firings, aiming at the final time, at the, that is final travel towards moon. Okay, so then here how many orbits, how to achieve all that also is an optimization problem to reaching the goal. So again we can use some optimization technique to use that to achieve the to realize the solution. Okay, so this is one of my students, he worked out this how to, the same Chandrayaan 2, more or less similar things. Chandrayaan 2 burns, when to start the burn, the epoch means that time is given here, what is the AEI after the burn and the mass after the burn, all these details I will not be going through this. Those who are interested later on can do this. Okay, this is a vehicle we used, that is Mark 3 vehicle, to get into the Earth parking orbit for the Chandrayaan 2 mission. Two solid, S200 means two solid stages, and a liquid stage 1 ton propellant liquid stage, and cryogenic engine of 25 tons. This is a total vehicle mass is here to 640, 43 meters tall, and liftoff was happening on this day. Why the actually injection is TLA injection, you would have seen 13th August. So 22nd to 13th August, so many firings happened. That is why it happened just prior to the thing. If it is not, if it is this type of firings are not there, we can lift off on 13th itself. Okay, that is the thing. So we got 170 by 45,000 orbit, and of course inclination was 21.46, and the AOP I said we used that as a constraint. Okay. And you can see in this slide, the orbiter, we had three elements here. Orbiter, the mass is 2379 kg, and lander 1471 kg, and then rover 27 kg. Land, of course, this is part of lander. This 27 kg is included here itself. Okay, this is a mass it carried into the parking orbit around Earth initially. Okay, this is just a glimpse of the integration in Sriharikota. Fine. Okay, this is all about the mission about Chandrayaan 2 reaching the moon and getting around this one. Okay, now we'll sometime we'll spend on how we landed, how to formulate the problem. I will quickly go through, and see, we with the Chandrayaan 2, it was put initially into 100 by 100 orbit around the moon. So we have to now separate the lander from the orbiter and then get down to the surface. Okay, so that process will not happen from 100 by 100 itself, because it will require more fuel. So instead, we first inject the spacecraft, the lander one into the another intermediate elliptical orbit. Maybe it may be 100 by 20, 100 by 15, 100 by 30, 100 by 40. In Chandrayaan 2, it was 100 by 30. It all depends upon the requirement. Many strategies we have to look at, to which will suit the many other aspects. Okay, which I am not addressing here. Okay, fine. So this is a thing. So we chosen 100 by 30 kilometer here, and from 30 it starts. We can see here the second step. Actually, from the 30 we will start braking. That braking means we have to kill the velocity, because initially in the 100 by 100 the velocity of the spacecraft will be about 1.6 kilometer per second, and when it gets down, it reaches this point, it has to be made zero. This is what I said. We have to achieve this to using the optimal control theory or direct approach or indirect approach, all that. So in between, just for for practical purposes, because if you simply say I end, the final orientation may not be suitable for leg down orientation. You have to just leg down, you have to that is vertically you have to get down and land. So for that we introduce in between another phase, we can say vertical descent phase. Up to this it will go into optimal phase. Orientation is fixed according to the optimal trajectory demand. Okay, and then it will be vertically it will be made and then start descent. This is a general scenario. Actually it will again vary mission to mission, depending upon the requirement we can vary. Okay, fine. So what is here disadvantage of moon is it does not have atmosphere. That is, of course, it's one way it is advantage also, because thermal point of view there is no friction on the surface of the spacecraft, so there is no drag. So there is no thermal requirements are comparatively less compared to atmospheric planets landing. But disadvantage is the reduction of velocity has to be done by propulsion system itself. Whereas if your drag is there, it will reduce the velocity as a frictional force. It will help us to, so you don't need to carry the chemical propulsion all the way there if atmosphere is there. Whereas in Moon's case, we have to reduce the whole velocity by thrusting only, through chemical propulsion means only. So that is a thing. Also, I have already told you that thrust direction and magnitude you have to continuously choose. So this way it becomes that because there is no atmosphere, about 50% of the spacecraft mass is lander mass is actually propulsion mass itself. Okay, this again I said you have to equations of motion. Just for your idea, I am giving you this is a planar case, not three-dimensional case. Okay, so these are V theta and VR are the components of horizontal and vertical components of the velocity. R theta, actually R and the theta, R cos theta, R sin theta is your XY components. So it is a planar case. You have to define the equations of motion like this. As I have told you, Chandrayaan principle, you have to introduce your co-state variables. They are given here. That is, there are here four state variables are there: R theta, V theta, VR in this case. So we introduce PR, P theta, PVR, PV theta, and also M dot also here one other co-state equation. So 5 co-state variables we introduce from the Hamiltonian, and then I will quickly go through. I will. Here, you have to formulate the co-state equations. I said Chandrayaan derived a co-state equation as dou H by dou state, actually dou X, dou Y, dou Z, like that. In this case, dou H by dou R is PR dot. You can derive all these things. And now finally, your optimal thrust angle is given by dou H by dou alpha equal to 0. You see here, finally, it turns out to be 2. It's a function. I already told you the design phase explaining. I told you that the control angle, this is thrust direction, is defined by alpha, is as a function of PVR, PV theta, which are co-states. If you are able to define this PVR and PV theta, initially you get that. This PVR, PV theta, all this I skip. Okay, this PVR and P theta is obtained by actually using some optimization technique. So many optimization technique, you can use so many optimization technique. There is what do you call differential evaluation is there, PSO is there, And the very familiar, very popular FMIN con is there, genetic algorithm is there, controlled random search. Like that, there are so many algorithms are available. Some are gradient based, some are non-gradient based. Whereas FMIN con is gradient based. And where DE, that is differential evaluation, PSO, and all, there are heuristic methods, we call them non-gradient based methods. Okay, so in general, gradient based methods require very good initial guess. FIN con will fail if you don't give close guesses for the unknown design variables. So that is one disadvantage of this. Whereas DE type of differential evaluation type of heuristic, they need only bounds for the unknown variables. You define a bound within which it is going to vary. The bound can be wide enough also. So you just start the process following Chandrayaan systematically, then you will get to the solution actually. Fine, okay. And this is many schemes we tried. Actually, these are all worked out by students. You can see the pros and cons are defined here. Of course. PSO, DE, all that. Finally, we concluded that differential evaluation for this landing purposes is the best method, which consumes less time, least time, and then least functional evaluations. Also, of course, final mass, landing mass, and that flight time almost more or less same with all other methods. Also, same for any method that has to be same. If it is different, then you have not got the optimal solution. All these are just how it started from. It is just a typical case of starting from 15 kilometer. It first rises and then comes out to zero. You see, this is a thrust direction. Thrust direction has to be set for the spacecraft lander according to this requirement. It starts with maybe around 165 degree and then slightly changes, and then there is a drastic change and then goes down like this. So it has to be set according to this curve. That is a requirement. Then how the horizontal velocity changes, how the vertical velocity, both will change. It will start from 1.61 kilometer and slowly it is killed and it is a zero here. And here vertical velocity, of course, initially itself is zero and then slowly builds up and then it comes to zero. Both has to be zero. Of course, these are all little extra details. Those who want to get into this problem understand I am giving the references here. You can get into these references. One was published in Journal of Earth System Sciences as back as 2005 in Chandrayaan one time, and this is the second one. Recently it got published. There are other papers also. These are all papers I am talking about to me and my students. Okay, yeah. Okay, this is a nominal profile for Chandrayaan 2. So starting, as I have told you, 1681 meter per second it started, and it ended up with 62 meter per second of vertical velocity and horizontal velocity of 146 meter per second at an altitude of around 7 kilometers. Then it started some phase to adjust the navigation here. Then it came that vertical phase we adjusted, and then it started vertically landing. And some problems happened, and we could not achieve the goal finally in just in a this one. Just little we could not do that setting. Okay, fine. So now I want to conclude any space mission optimization and achieving looking at the optimal design trajectory, the path is a integral part of all space missions, which we actually concentrated on this. So with this, I conclude my talk. Thank you. Now I am open to questions. I hope I could drive at least some of the important points in space mission design. Okay. Yeah. Thank you, all of you. Now I am open to questions. So maybe I have to minimize this. Yeah. Over to Aditya now to questions.
Thank you, sir, for your enlightening insights. So let's go towards the Q&A session. So the first question is, it's by Arya. When the probe lands on the moon, what and why will be there an impact if the final velocity is not zero? The probe is extremely negligible compared to the size of the moon. So how will it have the impact?
No, impact is whether on Earth or moon, Impact is impact. You throw a ball. So if you throw a rubber ball, doesn't no matter. But suppose you throw a ball with a lot of force against a wall, then what type of damage it will have, you can imagine, isn't it? The same thing. If you don't land with zero velocity there, then yes, it's all materials, some metals only, right? All spacecraft lander is made of some metals. So if you don't, if it made of rubber, yes, certainly what you may happen in future, whatever. So what even if you impact, it may not get damaged. Such things are going on in Mars mission. People tried with balloons, all that, some air filled, nitrogen filled balloons, and all these techniques are there. For landing in the moon, this type of technology with the legs down, all that. Yes, with propulsion, when we try with zero velocity is a requirement, is a must. Otherwise, yes, damage will happen to the thing. Yeah, fine. I think, hope it addresses your question.
All right.
Yeah.
The next question is by Swadhin. Does trajectory design takes uncertainties during flight into account in design phase?
Yeah, certainly it has to take. I was telling you initially we will design. We said no. I was telling you Lambert problem, right? First cut design will be there, and when we say we have to take care of all other planets are acting on the spacecraft, isn't it? They will be deviating the path, and I have told you that what you call non-spherical Earth. Earth is not sphere. That also we have to account for. These are all taken care of in the design phase itself. Okay, but there can be uncertainties, the deviation in the path due to propulsion system performance. Because the propulsion system may not perform as expected. After all of them are machines, isn't it? You cannot perfect performance. You cannot expect. Maybe 99.9% perfect. It can be. Nothing can be expected of 100%. So suppose I expect a specific impulse of for 400 meter per meter, 400 seconds. It may deliver finally 400.1 or 399 point. All these type of deviations can happen. So what do you think that you have imported 1.6 or 600 meter per second? Really, it would have imported 601, or it might have imported 599. So which will make the path deviate from its actual course. That's why we introduce mid-course maneuvers. Such deviations cannot be designed because propulsion system only when actually happens only we know. So for those things, we will be doing mid-course maneuvers, which will be computed how much path deviated will be actually through observations, through tracking. We will be getting the path, actual path, and the deviated path has to be pushed back to the actual path. So how much delta V is required for that, and how much propulsion and what direction firing has to be happen. All that modeling we will do it, and then it will be done. That will be that we call that process is called as trajectory correction maneuvers, TCM. Okay, all this will be happening. Okay, fine. Hope this addresses. Yeah.
So the third question is by Ayan. Related to aerodynamics, why do space shuttles does not take the pointy nose like most supersonic jets and having more like blunt nose should increase the drag? Is there some special reason for using?
No, you said aerodynamics only. That's the reason here actually. Such a huge mass. So aircraft is different. Aircraft is different. It's a small mass when compared to shuttle. Aircraft is nothing. It's the shape, and you said you have given your question itself. Answer is there. It is pure aerodynamics. Otherwise, your loads on the vehicle will be more, and it will break. It can break also, and the thermal effects will be intolerable, and it can have anything can happen. So that is why it's not possible to. But still, such things are research areas. They are all under development. Maybe after you may see that all of them in future. in maybe next 25 years. All this can happen. Whatever you talk about, it has to have to happen. Today, because of our limitations of technology, today's thing, they do not allow that, all that. Okay, fine. Yeah.
Yes, sir. So the next question is by Manoj. Why is the gravity turn trajectories are not always the most efficient possible launch, even though they use minimal steering thrust?
Okay, gravity turn is not actually. I already told you we have to reach a target. Okay, gravity turn may not achieve the target perfectly. That is the one thing. Like, because gravity turn means you are aligning the always the thrust and velocity in the same direction. Angle of attack is zero. That is the one thing, important thing you should note down. That I have already told you, to reach the target, we need time to time we have to vary the orientation. That varying the orientation may not be the, sometimes by luck it may happen to be gravity turn. Many times it will not be. So if you want to achieve a particular target perfectly, you have to go for optimal orientation only. Not gravity turn always will not help you. But gravity turn some will help. In Apollo, they did the gravity turn. Why? They were able to vary the thrust. Instead of varying the orientation of the vehicle, they varied the thrust level itself to the, I will give only this orientation. You tell me, I can always formulate the problem and get the, what is the thrust level required to maintain gravity turn. But that requires a very high level of variability of thrust and engine capability, all that. Okay, so what you said, as of now, gravity, with the gravity turn alone, it's possible to achieve orbit, but subject to again technology limitations. Otherwise, with the present technology, commonly publicly available technologies, what we use actually, we have to orient according to this one requirement, because thrust is only limited variation only we can do. Sometimes, most of the times, constant thrust is always advantageous. So that way, we cannot go for gravity turn always, which will not achieve us the target. Okay, perfectly.
So the next question is by Nidhi. As we have recently heard about HSTDV, which placed India at an elite position, mainly because of its speed. So why does the speed of missile matters a lot?
Okay. This is related to missile. Of course, I can give you a general knowledge answer only. I cannot give the right answer for this. Why speed of the missile matters a lot. You actually ask, it's a strategic thing. Why you can always uh, guess an answer for this. These are all defense related things. Okay, you can guess an answer for this. Maybe you can call me later on. Okay, fine. Yeah, maybe I'll take the next question.
All right, sir. The next question is by Kishore. What is the range of thrust required for 1U cubes at altitude control? And what's your view about conspiracy theory of moon landing?
Okay, first question I can answer. Conspiracy theory, I do not know. Okay, the range of thrust you require for a small this one U CubeSat and all, about 10 Newton to 20 Newton is sufficient. Control thrusters. Okay, that you have to design a control thruster which will deliver about 10 to 20 newtons. Even 1 Newton also is okay. It all depends. The what type of requirement is there. If it can vary from 1 Newton to 20 Newton, that is more than that. I think, to my knowledge, I have not come across. I don't foresee any requirement. Of course, I already told you any design is depends on the requirement only. So you may have some special requirement. If I say it never 20, that statement can be wrong also. Sometimes depending upon your requirement, it may exceed also. But in general, 1 to 20 is fine. But about conspiracy theory, these are all, this all we can take films and watch. That is the only thing I can talk about. So we will not answer that question. They will We have, see, Apollo is a reality, isn't it? Yes, but it's a reality. It has landed, and we have also gone and landed. Only thing, you will ask how whether humans, Apollo, listen, that's a different story. All that you will ask. I don't believe this conspiracy theory personally. Okay, I believe yes, all that happened. Okay, fine. We will go to next question. Yeah.
The next question: uh, how do we place multiple satellites like 100 by ISRO using one spacecraft? How likely is it
Yeah.
feasible?
Yeah, fine. Yeah. See, with 100 actually, we have to push. What is the main problem when you push multiple satellites? So we are injecting satellite with very, very minimum impulse, spring system only, which will impart the velocity difference between the injected one and the main satellite will be some 0.5 meter per second or 1 meter per second only. So with that, what will it may come back and hit also. The main problem is actually you have to choose the orientation of injection and the with what spring action you are separating them, with what separation system you are doing that. Once it is done, no issue at all. You can do any number of satellites. Only thing you have to have housing. We call it housing. We have to place the satellites for 100 satellites. They are placed in clusters. All these 100 satellites are placed in clusters. Like the 10 together, 12 together, 15 together, like that it is placed. And they are all injected in different directions. And that is possible. And actually, you can, if you are interested, you can go through a paper by me in 98, I think, multiple satellite lines by a single vehicle in Journal of Guidance, Control and Dynamics. I don't remember the exact title now. This is about, I think, at least keywords of multiple satellites, Ramanan, Journal of Guidance and Control. Certainly will give that will give you further what are the important design parameters which makes it go into different orbits, which avoids future collision. They will not come into contact again. All that paper addresses. Maybe you can go through that. Okay, fine. Yeah.
Yes,
Yeah.
sir.
Next question. Yeah. Yeah. Space debris is increasing every day.
Yes, sir.
Yeah. Does it cause any problem in mission? Yes, certainly. We every launch we go through, because launch, that it reaches from starts from surface, it reaches 600 kilometer or 700 kilometers. When the vehicle is going, some debris may come in the path of the trajectory of the launch vehicle. It may come. We cannot rule out. So we always conduct a study whether any debris comes. If so, we delay by fraction of some second, 1 second this side or that side, so launch liftoff itself. So that is sufficient actually. Fraction of a second is sufficient so that the distance it will go away or it will not. We will cross before that fellow comes. All these studies are done actually. Yes. State degrees that cause a problem to launch vehicle, though it is not very severe as of now. In future it may also, but we take care of them. Every launch is taking care of the debris actually, debris evolution also. Okay, yeah.
Okay, sir. So that was the last of the Q&A session. Last question.
Yeah.
Thank you, sir. We really enjoyed the session a lot, and we're fortunate to hear it live from your side, sir. So,
Okay,
guys,
fine.
we have reached to the end of our first webinar of the Primus 2020 series. But wait, we're coming up with more super exciting webinars in the upcoming future in the Primus 2020 series. So please subscribe our channel and press on the bell icon as well. Stay tuned to our social media handles mentioned in the description below, and join us in our quest to unravel more answers to our space curiosity. Till then, space out.